Welcome to today's Yara webinar titled Fertiliser Quality, a Risky Business. I'm delighted to be joined by my two colleagues, Natalie Wood and Philip Cosgrave. Now, both my colleagues there have specialist areas by way of cropping, but today's webinar is very much about fertiliser quality. And of course, fertiliser quality is really irrelevant of the crop, because the issues associated with it are very much common across crops. So today we thought it was appropriate that we split the subject matter down and tackled the two sort of components or elements of fertilizer quality that we recognize, which is the sort of chemical attributes that we see, and Natalie Wood will go through the chemical attributes of fertilizer quality. And then Philip will take us through the physical attributes and how they can have an impact. But by way of just introduction, then I thought it was worth just thinking about why fertiliser quality really does matter. It's always been a topic of interest, of course, and certainly over the 20 years I've had with Yara, it's been a common thread throughout those years. But when the values of the fertiliser are so high now, then it becomes ever more important as a subject to really consider. When I mention values, then I mean their crop and fertiliser, of course, because on the one hand, with the high value of fertiliser, then you should really expect the best quality when you're paying the sort of amounts that are out there now. So you really want to be getting the best quality possible for that value. But then, of course, there's the crop value. And there I'm thinking whether it's a ton of wheat or a litre of milk, then the yield becomes ever more valuable to attain, and getting the response and the return on the investment from that fertiliser with that high yield and quality then becomes so important. So what does it entail? As I've said, then we've got the chemical composition associated with it. So Natalie will go into the detail there in terms of how that needs to be thought through, and then the physical composition, Philip will enter into that sort of discussion. I think there's a third element now which comes more to the fore, and that's the environmental credentials when it comes to fertiliser quality. So there I'm thinking emissions in terms of how that can impact the environment, but also now the carbon footprint itself. Something that's new that I can just happily share today is the Carbon Connect from Yara, which is where we can now get verified carbon statements for products that we supply from specific factories that come into UK and Ireland agriculture. So Carbon Connect is something to look out for there, and get in touch with us about if it's of interest. But yeah, environmental credentials more important as well now in terms of when considering fertiliser quality. I think over the years we've focused on some of the issues and have done surveys throughout the time. And when we've done those surveys, we do come up with some quite startling results, which again really highlight the importance of fertiliser quality and the sort of aspects that we can include there. And we've got those sort of legal requirements of bag weight. So when you buy that fertiliser, you should get, and you certainly should expect to get, the exact weight that you bought. Sadly, when we've done surveys, then we still see that 38% of those bags are underweight. So you're not getting value for money from that bag weight. Nutrient analysis, clearly a critical point when it comes to making crop nutrition plans and fertiliser recommendations. Then you want to know that the analysis is correct and what you've bought is in that bag. So sadly, those surveys over the years have again highlighted that 39% have failed to meet that correct declaration. So another really key aspect when it comes to getting value for money. Of course, storability and traceability are areas that are still there as very relevant. And again, we see that bag liner thickness and traceability do fall rather short when it comes to those aspects of the fertilizer that you're buying. So again, some areas there highlighted which show that fertilizer quality really does matter, and that you should be thinking giving very careful consideration towards it when purchasing. During those last few years, as I've mentioned as well, we've seen how we've commented on aggregation of marginal gain, particularly noted around the Olympics when it was in London that year, 2012, and that whole concept of achieving elite performance coming from aggregation of marginal gain, where we look at all the small components and they incrementally improve to bring that reliable, resilient, world-class performance. Now, of course, that works in reverse, and when we start cutting corners or perhaps compromising on some of the management practices we do, whether it's the inputs or even actually being rather more reactive as opposed to proactive with some of our input decisions, then it can become that aggregation of marginal error where we start to introduce risk and start to maybe bring in errors and problems that just start to undermine that sort of requirement to achieve that world-class performance that we want. So yeah, it does work in reverse. So as we start to undo some of our management practices with poor decision making, then we can introduce error there. And a final reminder that we've over the years again talked about prevention is better than cure mantra that we've had, whether it's through analysis that we do, but it's very applicable again to fertilizer quality, that you can really be introducing problems rather than thinking about it proactively and preventing those quality issues and the related sort of problems that come from that coming into your farming practice. So prevention better than cure is again something we should strive for when it comes to considering fertilizer quality. So in that sense, I'm going to hand over to Natalie now to take us through the chemical attributes of fertilizer. Philip will then follow that on with the physical characteristics to be considering, and then I'll just close out with a summary at the end. So yeah, over to you, Natalie.
Thanks, Mark. As mentioned, I'm going to cover some of the important chemical attributes of fertilizer and how choosing specific properties can help you to mitigate some of those risks and potentially the ones that you can then control. So if we start with availability of nutrients, we want to apply things that are immediately available, and especially at that first time in the spring. And I've put here 8. And what I mean by that is we want to think of nitrate, sulphate, phosphate, because that's the plant available form. We see ever more extreme weather conditions, with dry springs becoming more common than wet ones. And if we think of this in particular, dry weather in the spring can mean that crops, need to be more resilient than ever, really, to cope with that lack of moisture. So this requires the crop to have a good root system that's large enough to access those water and nutrients. And if we can help that by having immediately available nutrients in that 8 form, as I've mentioned there, then we're not going to kind of stop that crop momentum. We've got the nitrogen cycle here. So if we look at that in particular, the AN side, you can see that green arrow is the nitrate, which immediately goes through to crop uptake. And then, of course, you've got the ammonium aspect, which has to break down with the blue arrow there to become nitrate. But you can see that the nitrate form of the ammonium nitrate is immediately available there. Calcium nitrate is the most available form, which is obviously 100% nitrate, but it's not economical on combinable crops, which is why the next forms, such as the ammonium nitrate, urea ammonium nitrate, and calcium ammonium nitrate, are the ones that we want, really, because they are going to be immediately plant available. What we also want to do is not hinder this crop at all. So that's what we have, these immediately available forms. And then, once crops start to grow in the spring, we've got that focus on getting the nutrients straight into the crop there. If we look at the other side of that nitrogen cycle, then we've got urea, of course. Urea isn't immediately plant available because it has to undergo a 2-stage conversion in the soil before they can become nitrates. And so, yeah, obviously it's not going to be immediately available. The first conversion to ammonium is relatively quick. It only takes a few days. However, depending on the soil conditions, the second phase of the conversion from ammonium to nitrate can take up to 6 weeks, particularly in cold conditions. So when we're thinking of using urea at that first timing, you know, it could take longer than you're expecting if the conditions are cold, for example. And if we look at this here, then we've got different trials over a long amount of time. You can see there 236 trials altogether. And you can see the green side is where ammonium nitrate has outperformed urea, and then the grey side on the right hand side is where urea has outperformed AN, but you can see 2/3 of the time then AN comes out on top. So it's just thinking about things like this. Product choice is going to impact upon when that crop gets those nutrients, and it's just bearing things like this in mind so that, you know, you're not caught out come spring thinking that you're going to have immediately available nitrogen. Urea, you know, it's well known that we will lose up to 20% of the nitrogen in the form of ammonia following an application of urea. If we compare that to ammonium nitrate, that's only 3%. You know, so what we're doing here is introducing risk rather than mitigating it. If the ammonia is lost to the atmosphere, you know, it's not contributing at all to yield or quality or obviously then crop productivity. So on top of that as well, we're also increasing the environmental issue of ammonia losses into the atmosphere, which has that knock-on effect to, you know, human, animal and ecosystem health around the country. If we have a look a bit at ammonia emissions, you know, we can compare the different sources of nitrogen, and there are some quite big differences in the ammonia emissions to the atmosphere. If we look at this data here, this is the NT26 data, and you can see the average emission factors from urea, which is the red column. You know, they're 8 times higher than the AN, which is the darker blue column towards the right-hand side. And if you look at that green column next to urea, that's urea plus an inhibitor, and you can see there's still twice as many emissions from that treated urea when you compare it to the AN down at 3. So just another thing to think about when we're looking at product choice. This is looking at some different soil types as well. So if you are on a calcareous soil, you are going to have even higher emissions. If we're looking at the temperate green bars, which is obviously more comparable to our climate, you can see there's an increase there on most of the emissions on the calcareous soil. So another thing just to bear in mind, really. If we're looking at the carbon footprint as well of different products, that's also a consideration. You know, a lot of people now have got strict net zero carbon targets to meet, and this is only going to come down the chain to farmers. You can see here on the left-hand side the different production methods of ammonium nitrate giving different CO2 emissions. In the blue, you can see that the EU factories have Yara's abatement technology, which has been around a few decades now, and that gives us the lowest carbon footprint when you compare that to the CIS, which is Russia, Ukraine, etc., North America, and then the CN is China. So you can see there's a massive difference there between the emissions, between the carbon footprint, sorry. If we look at the right-hand side, we've got urea here, and it's a similar story in terms of the European being the lowest level. As well, the green section you can see is we have to add on the hydrolysis of urea once it comes into contact with the soil. So that's what you see by the 1.59 there. So yeah, when we're thinking of importing urea, you know, just we have to bear in mind that some of those imports are going to have a higher carbon footprint, which I guess you might not be so interested in now, but it's only going to become more and more important as time goes by. So if we look at inhibitors, obviously there is the urease inhibitor, or MBPT, which is, you know, it's been around a very long time, and it is introduced as a way of reducing the amount of ammonia that's lost. Yes, it is very effective at reducing the ammonia loss, but also, you know, what we're doing is inhibiting that process that we are trying to, you know, that we don't want to do. So we're inhibiting turning that unavailable urea into available nitrate nitrogen. So that's just another thing to think about. It will slow that process if you are using an inhibitor there. So again, it's just back to that risk management and how product choice can make a big difference in terms of availability of nitrate, etc. As I mentioned, another 8, so we're on to sulphate now, and it's the same story as nitrogen. So we nitrates from nitrogen and sulphates from sulfur are the plant available forms. What we don't want to do again is slow that growth momentum. So we need to make sure that that sulfur is immediately available to the crop, which it means it has to be in that sulphate form. And also we know there's that relationship. So nitrogen needs the sulfur in order to be taken up efficiently. And so we need both of those nutrients there. We know that the demand is in the spring, so therefore we should be applying it in the spring, but we don't want to apply it in one go. So we don't want to dump one lot of sulfur on. We need to apply it little and often, and we've mentioned this a lot of times in the past, but because of that relationship between the two nutrients in the plant, it's always advisable really to have some sulfur when you apply the nitrogen. So that means an NS or an NPKS product, you know, at all fertilizer timings. And this is a trial here just showing how all early compared to little and often, you know, it does make a difference there. So phosphate, of course, is another key nutrient. And the source of the phosphate does have an effect on the availability to the crop. We can start to manipulate it more by understanding a bit more about the properties of the different types. You know, there's several factors that affect the uptake of phosphate in the soil, such as pH, temperature, etc. So we need to bear those in mind when we think of product choice. There's 3 different forms of phosphate. There's orthophosphate. This is immediately available to the plant because it's water soluble. So that's, yeah, good source of immediately available phosphate. There's polyphosphate, which is basically a long chain of orthophosphate. So it takes a little time for that to break down into orthophosphate. So, you know, you've got a bit longer availability there because it's taken longer to break down. We've also then got the dicalcium phosphate, or DCP. This isn't water soluble, it's actually citrate soluble. So citric acid is in the plant root exudates, so they put those acids out when they're actively looking for nutrients. And this means that DCP becomes available when the crop wants it because it has to be broken down by that citric acid. If we look at the different types of products that we've got out there, you can see that MAP, DAP, TSP and other NPKs that are out there are almost 100% orthophosphate, so they're immediately available. If we look at the Yara products there, granular and prills, there's a slight difference there, but you can see we've got a combination of ortho plus DCP or ortho, DCP and polyphosphate. But why is that important? Immediately available sounds great for the orthophosphate, but if we look at this graph here, this is looking at P in the soil solution, which is where the plants can access it, and it reduces over time after an application of orthophosphate. So you can see that 40% is lost in a short space of time and has become unavailable to the plant. Because it's no longer in that soil solution phase. It's probably been fixed with iron or aluminium ions or precipitated out with calcium ions. So really it's understanding the type of phosphate and what that can bring to the table. So whilst it's good to have immediately available phosphate in the product, you know, it isn't able to take the phosphate up quickly enough to make the most out of it. So it's quite inefficient. I think only around 10% efficient. Therefore, if you've got that mixture, you know, you're much better off. And if we look at what we call P-Extend, which is our combination of ortho plus DCP or ortho DCP and poly, if you've got several types of phosphate present, you're going to increase that length of time that the phosphate is available to the plant. You've got greater availability for a much longer period of time, as shown on this graph. So you can see there's still phosphate being released 73 days after here. This is in winter wheat. You know, it's supplying that crop through that peak demand for phosphate, which is again in the spring. And you can see as well there the DCP fraction of it isn't absorbed by iron or aluminium. So, you know, it's not going to fixate with anything DCP until that plant puts out those exudates. You know, we know as well that in terms of increasing efficiency, we want to put those nutrients on when the crop actually requires them. So you can see from this that the demand for phosphate is very low until we reach that March through to May period. You know, so using the information that we know about phosphate availability being low in cold soils and crop demand timing as well, it enables us to apply available phosphate when the crop requires it, and we're increasing that nutrient uptake efficiency greatly by, you know, applying it when it's needed, applying the right type of product, etc. So, you know, we always say around 35 to 50 kilos of fresh P and K. You know, you're ensuring that the nutrients are available when the crop requires them. The crop starts growing at 5 degrees, whereas the availability of phosphate is very low until, say, around 8 degrees onwards. So it's making sure we've got that fresh supply. And independent trials results have shown that, you know, you can get 0.3 tonnes per hectare yield increase from that fresh application in the spring. But overall as well, we're increasing the whole nutrient efficiency of all the nutrients by, you know, using them smartly when they are required. So to summarise just the chemical aspects, use the information that we know about these chemical properties, in particular of the fertiliser and the soil, to your advantage so that you are working smart with them. Mitigate risks by choosing products based on their qualities, such as the plant availability, less losses to the atmosphere, season-long supply of nutrients, and then reduce environmental impact where we can with products with lower carbon footprint and the lowest ammonia emissions. So I'll hand over now to Philip, who's going to talk about some of the physical attributes of fertiliser.
Thanks very much, Natalie. And in this section, we're going to discover the physical attributes of fertiliser. And we're looking at I suppose, the quality of the fertiliser and then actually the spreading of it as well. And these are dependent components, but they're often overlooked in the whole process. So as Natalie has described and has gone through the actual, you know, the important aspects of the actual chemical composition of the nutrients we're using, you know, it's also important to recognize the importance of the actual physical quality of the fertiliser we're using, but also then the application of it. And I guess this would be a typical scheme of what might go through a kind of a process of what a farmer might decide to do. They might do soil testing, then they will come up with a nutrient recommendation, and then purchase a fertiliser product to deliver that nutrient recommendation and then apply it. But certainly, I think it needs to be the last two parts of that equation need to be are as important as the previous two. So why do we want an even spreading of our nutrients? Well, number one, it's a regulatory requirements in both in most jurisdictions in both the UK and Ireland. And machine design, I suppose, has come on a long way in the last 15 to 20 years. So now new machines are capable of spreading fertiliser from, you know, 24 meters out as far as 42 meters. But there's one thing about the capability of the machines that are spreading this fertiliser, but what we must consider is the capability of the fertiliser we're using to be able to be spread at those wider distances. And obviously the physical characteristics of the fertiliser have an important part to play in even spreading. You know, machine settings is another thing as we go on now to the actual machine itself and the spreader itself. So we're looking at, you know, the machine settings. You know, there a lot of these fertilisers, in particular Yara, send products to all the major spreader manufacturers so that it can actually be tested, so that we can actually have accurate settings for all our individual products. And some of our products are made in a number of different factories. For example, Yara Axan is made in 3 different factories, but we also send product from each one of those factories for testing to those spreader manufacturers. So then in their actual, the apps or the settings books that accompany new spreaders, that there will actually be a setting for Axan from each individual plant that manufactures that Axan. And also we must take into account field conditions, wind, humidity, and that will affect different fertilizers in that when the weather conditions, when the fertilizer is being spread, particularly in the springtime when there's going to be more humidity, it's more, and probably likely to be a little bit windier as well, that will have an impact on how well that fertilizer can be spread. So, and obviously, how can we assess the evenness of spread of a particular fertilizer? And this is where we look at the coefficient of variation, or CV. So we assess this by doing tray testing, but tray testing has its limitations, particularly when we're looking at for certain products that contain, particularly blended products that have different components within that fertilizer. So if we look at something like a nitrogen and sulfur product, so you may have different components one component making up the nitrogen source and one component making up the actual sulfur source. And then also then with NPKS products, there can be there can be up to 4 different products making up an NPKS blend. Now this is not a limitation when it comes to Yara products, because Yara products are true uniform compounds, or CCF products. So basically they have very the physical characteristics are the same for each granule, but in blends this is a limitation in that each particular component has different physical attributes, so that will affect the spreading pattern of that individual fertilizer, that particular fertilizer. And we look at a CV. We would like to see CVs of less than 15 at most, but we would prefer to see them at 10 or even at 5. So the more accurate we're spreading them, well then obviously that's better for the crops that we're applying them on. Now farmers can look at testing their spreaders and getting their farmers kind of get them tested annually, and the national sprayer testing scheme also tests spreaders. And we would encourage farmers to actually go and get their spreaders tested on a regular basis and on an annual basis. Now this is just a survey from 2020 of grassland farmers, and 37% of respondents didn't check settings regularly, and 12% use the testing service. So there's lots of scope there for an improvement in testing our spreaders on a regular basis, but also of actually looking at the actual spreader settings and using the settings for the particular product we're using. So what are the likely losses of uneven spreading? So if we look at particularly winter wheat here, if we look at a CV of 15%, we're looking at a likely yield loss of 0.6%. Now 0.6% on a 10-ton crop is 60 kgs, which at a wheat price of say £250 per tonne, that equates to £15 of a yield loss per hectare. But when we look at it at very high CVs of 30%, you're looking at a yield loss of 2.3%, and that's 230 kgs of grain on a 10-ton crop. So you're looking at between 55 and 60 pounds of a loss there, and that's kind of a scenario. And obviously you can see there with lodging, and as we go further at a 50% CV, that the actual losses are quite extreme, and they're quite similar for winter wheat and winter barley and spring barley. And obviously for oilseed rape, the actual CV has a more important part to play in oilseed rape crops. We can see there at a 15% CV, we're losing 0.9% of our yield due to an uneven spreading pattern. And what are the fertilizer quality characteristics that we should be looking at? These physical characteristics. So it's bulk density. That's basically the weight for a given volume. So it's basically kg is the unit we use, and liters is the volume we use for that. So size and shape and hardness, and I'll go through these now individually later on, but also we'll go through straights, blends and compounds, and what actually makes up what to look for in actual physical quality in those particular products. So bulk density. So high bulk density, this is kind of the analogy we use as a golf ball versus a table tennis ball, whereas your golf ball has a high bulk density and your table tennis ball has a low bulk density. They're roughly about the same size, but obviously you can throw a golf ball a lot further than you can throw a table tennis ball. And one of the most important factors for good spreading performance in using fertilizers is to use fertilizers with a high bulk density. As products with a good bulk density weight, a high bulk density or specific weight, as it's also called, achieve desired throwing widths more easily. Now the next thing is the size range. So I've used the same size range as many farmers would have. So they may have a little grader box that they can actually test for this, and this is the actual breakdown of the individual compartments in that size range box that they may have. So you've got less than 2 millimeters, and then you have 2 to 3.3 millimeters, and then between 3.34 and 4.75 millimeters, and then above. But we would like to see the vast majority and 100% of our particles kind of falling within this range, and preferably, between the 2/3 coming in between 3.3 and 4.75. We don't want to see anything less than 2, and we don't like to see anything less than 5. Because so this diameter range, so differently sized granules are deposited more randomly behind the spreader, and this way the granular size range has a positive effect on that lateral distribution of the actual fertilizer. So the shape is something that we probably can't measure. I'm sure there is ways that it can be measured, but generally on farm, we don't measure the actual shape, but we're looking at the actual just purely visually. So we've got MOP there on the left-hand side, which is a very angular crystalline product, versus a Yara product on the right-hand side. So you can see the differences. One is spherical, the other one is granular, and that will affect actual how that comes off the veins of the fertilizer spreader, in that your granular products, the rounder shaped products, flow off the veins in a more predictable fashion, whereas angular products don't flow off the veins nearly as predictable as rounder products. So hardness, very important one also. So you need a granule that can withstand handling. So it's just purely from the loading into the actual fertilizer bags at the bagging plants, but also then that it can stand then being opened, and it can withstand the flow through the actual fertilizer spreader and the actual impact of the spreader veins. And this is when it comes to getting wider distances or spreading distances, this becomes even more important, because what you don't want, if you're spreading at 36 meters, the impact of the actual granules or the fertilizer particles on the veins can actually shatter the particles. So, shatter creates dust and less predictable spread patterns. And also granular or prill. Well, there's granular, there's no real difference, but the important thing is not so much that it's a granular or prill, but it's actual physical quality of that granular or prill. So pretty much you're looking for prills that meet the actual size range previously, but also have got a bulk density, of in and around 1 kg per litre. So we can see on the extreme right, they're prills, but they're very small prills. So there's a lot of them, below that, that less than 2 millimeters in size of a diameter. So they're going to be increasingly harder to apply over wider distances. So we look now at the composition. So this is looking at, we'll look at blends first. So components have different physical characteristics. We look at individual components. So on the kind of the diagram on the right-hand side, we see there that each individual component has a different kind of spreading width. If we look at mixing them, at blending them together. So generally the urea is generally going to be probably smaller in size. It has a lower bulk density, and you're not going to be able to spread that over the same distances as something like MOP that has a higher bulk density of in and around about 1 kg per litre. and then DAP then kind of falls in between. So you're looking at, particularly with blends, it's even important to actually look at what the individual components of that blend. And like urea blends, I put 2 question marks after the urea blends, but they offer, they are very problematic for spreaders to apply evenly, because there's such a big difference between the urea and the other components that are making up the P, K, and S factors, components in that particular blend. So that needs to be watched out for, and farmers need to be aware of that. If they're using NPKS blends, that they ask that particular question, is there urea in it, because that will impact the actual evenness of spread. But the other thing what we have with blends is that we have fewer landing sites. So generally, DAP example is a very concentrated phosphate source, so we don't actually have to put a huge amount of that DAP into the actual product to actually have if we look at something like a 2755, we need to put very little DAP into that product to deliver that 5% phosphate, or P2O5. So that means that there's way less landing sites of phosphate than there is of some of the other nutrients within that particular blend. So we really have these uneven spreading patterns. But one thing we may recognize, that say we're obviously aware of the impact of nitrogen and sulfur in creating striping, if it's being if there's an uneven application. But what's more subtle is the actual uneven application of potash and phosphate, because it's unlikely that we're going to see that in the actual crop, even when they're being when there's CVs, very high CVs there, so very poor spread patterns. With true uniform compounds or complex compound fertilizers, there's no segregation in the actual product. All of the nutrients are contained within each granule. Particles have similar spread patterns, and you have a maximum number of landing sites per nutrient. So you're getting, you're moving away from that risk of using blends when you're using these true uniform compounds. That each individual granule has the same bulk density, it has the same hardness, it has the same, the size range will be also, within that 2 to 4.75 millimeters diameter. So you've got all those physical characteristics. So you've got a product that is easier to apply from a spreader perspective. So if we look at the P and K landing sites, this is just where we're comparing a 2755 product using DAP as a phosphate source and something like Yara Mila extra grass. So when we look at this, we've got 10 times more landing sites per nutrient by using a true uniform compound like extra grass in comparison to a blended equivalent. So the other thing, I suppose, with the Yara products is that we have settings for those products, and I guess it's important for farmers then to actually use that setting, whatever product they're using, that they check the setting for that product, and then they set their spreader for that accordingly. So you'll find the actual product code either on the front of the bag or on the inside liner, on the label on the inside liner at the top of the bag. And that's important to pick that code out and then to actually find the spreader setting for that product. If we go on to the next step here, these are just 2 screenshots from 2 spreaders. So we've got the Amazon on the left, and we've got the Roucher on the right hand side. So we can see here that we can actually identify the product we're using, not just by the product name as it's known by, say in this instance Yara Mil Activa S, but also then from the actual product code. So just a summary of the key points that I've covered. Service and test spreaders annually. Select the correct fertilizer product and apply it accurately at the correct rate and timing. Use the correct spreader settings every time and tray test, but obviously be aware that the tray test is just accounting for the evenness of the whole product, may not show the actual CV of each individual component within that product, particularly, well, if it's a blended product, but with a Yara product, you know that the actual CV is the actual CV for each individual nutrient within that product. And then focus on value and not price, and select the best physical quality fertilizers available, because there's no point in buying a fertilizer on price and then it can't be spread evenly for your crop. Thank you, and I'm now going to pass back to Mark now to sum up.
Great, thank you very much, Natalie and Philip, for those two presentations, really covering very thoroughly there all those properties that we talk about chemically and physically. Notably from Natalie's there, that issue associated with introducing risk into the program when you're choosing fertilizer quality there, and products that contain that urea, whether it is just urea sulfur, or urea NPK blends, as Philip mentioned. Then urea is urea, and it has those challenges associated with it in terms of immediate availability or not, as the case may be. So really important to focus on those chemical properties. And then, yeah, Philip covering the physical ones well there, from just that aspect of getting spreaders tested, and then using the correct grade code. But then the attributes when it comes to that Yara compounds, which give you that maximum number of landing sites, so that you've got not only available nutrient, but maximum landing sites of available nutrients to give the best chance of meeting that crop demand, whether it's wheat or grass or oilseed, to perform as it goes through the spring and summer months. So some really critical components there that have been summarised. I think it is, without a doubt, farming is risky enough at the moment without introducing even more through use of poor fertiliser quality. So yeah, do think about that mantra again: prevention is better than cure. Then when you make that fertiliser choice and you're in buying, then ask all the detailed questions. What's in it? What are the chemicals in there in terms of urea, sulfur, etc.? Find that out, because they come with, there's some challenges there, and you can see on the top of the screen. I think when you look at the different qualities, then you can make the decision yourself in terms of what would you rather use in terms of that nice even fertilizer quality from Yara versus some of those blends that are out there in the market. You can see the bottom left as well, and that was a drone shot taken from this last spring when we saw with very visually there the impacts of accuracy of application. And there again, Philip mentioning the physical characteristics to get that coefficient of variation as low as you possibly can. In that picture, of course, you can see it was through a liquid application, which arguably gives that real ultimate accuracy. But accuracy itself is so important in terms of getting that nutrient spread. So again, fertilizer having an impact there. And then finally, do look out for the quality mark from Yara, in that we do have the saying that what's on the bag is in the bag, and we truly mean that when it comes to purchasing Yara products, that we do have that guarantee there of analysis. So when you are making that purchase, you know exactly what you're getting, and therefore exactly how your crops are going to respond. So that's it for the webinar today. Thank you very much for listening in, and I'm sure we'll again see you on future webinars. Thank you very much, and goodbye.